if we're graphing position versus energy, specifically position versus potential energy, but the whole idea of graphs of energy is that all the types of energy, potential energy of any type, kinetic energy, whether it's translational or rotational, thermal energy, bond energy, even total energy, they're all measured in the same units, joules. So that means we can graph them all on the same axes. So it's a very useful way of comparing all these types of energy. Like if you were looking at, for instance, the position of the object and the velocity of the object and the temperature of the object, those are all measured in different units. So there's no way you can put them on the same graph. But if you take all of these indicators and convert them into energies, energies are all the same units, so you can graph them all together. Very useful way of comparing those values. But let's take a specific look at potential energy. If you've got a graph of potential energy, for example, let's say spring potential energy in particular. What's our usual formula for spring potential energy? Yeah, 1/2 kx squared. Half the spring constant times displacement squared. So let's say x in this case represents the displacement of the spring. X represents how far the spring has been stretched or compressed. Generally, we treat 0 as equilibrium, positive values as the spring being stretched, and negative values as the spring being compressed. So that means we will actually want to include both positive and negative x values. So let me actually graph this with the energy axis more towards the center. Also, whether x is positive or negative, we're going to be squaring it. What does it tell you about the result of potential energy here? What sort of values can you get for spring potential energy? Well, when you take any value, whether it's positive or negative, what happens when you square it? Yeah, it's always going to be positive. So that means for spring potential energy, the result will always be non-negative. You could have 0 if x is 0. If x is positive or negative, you get a positive result. So spring potential energy in particular can never be negative. Other types of potential energy can be negative. For instance, gravitational potential energy. It's entirely possible for y to be negative because y just represents your height as compared to some reference point. Like let's say we call the ground y equals 0. If you're on the ground, you're at height 0, so your potential energy is 0. If you're above the ground, your potential energy is positive. But if you dig a hole and go underground, you're below 0. You're below that reference point. So your y value will be negative and your potential energy will also be negative. So it's entirely possible for a potential energy of gravity to be a negative value. And other types of potential energy may be positive or negative as well. But spring potential energy, because of the way we define it in the first place, is never going to be negative. Any questions on that so far? And let's say we want to graph potential energy and kinetic energy on the same graph. What's our usual formula for kinetic energy?
One-half mv or m delta v squared.
Yeah, or I would actually not include the delta here because in this context, when we're talking about a graph, we're not really talking about the change in energy. We actually are looking for what's the energy at that instant. So like at this location, we want to know what's the energy. And also at this location, what's the energy? And at this location, what's the energy? So in the context of this graph, we are typically looking for what's the energy at each instant. So we've got half the mass times the speed right now squared. As opposed to if we were looking for how much the kinetic energy changes from one instant to another, then we'd look at half the mass times change in speed squared. However, the fact that we've got a speed squared here means it doesn't matter whether the velocity is positive or negative. It doesn't matter whether you're moving to the left or moving to the right. The result is always going to be non-negative. You can't have a negative kinetic energy. It can be 0 if you're not moving, even if you just come to a stop for an instant. Like let's say you're moving in one direction, slow down, come to a stop, and bounce back. At that instant, when you come to a stop, your kinetic energy is 0. But you can't have a negative value for kinetic energy because mass, of course, is never going to be negative, and speed squared is never going to be negative unless speed is an imaginary number, but that doesn't really make any sense anyway. So both of these, kinetic energy in general and potential energy specifically of a spring, are never negative numbers, which means if we're graphing both of these and that's it, we don't need to include any negative values of energy on the graph. So we can save some space here by just having x-axis in both positive and negative directions, and energy axis, we only need to include the positive direction. So let's try graphing this. If you graph k over 2 times x squared, what sort of shape would you expect that to be? If you just have constant times x squared. Yeah, this is going to be a parabola. You've got the, if you think of potential energy as the output, and you could kind of think of this as x and y, but I would recommend trying to move away from thinking of the axes as always x-axis and y-axis, because these could be labeled with any variables you want, depending on what you're actually measuring. So I would try thinking of it as the input and the output. The input in this case is where you are. The output is how much energy you have at that instant. So output equals a constant times the input squared. And anytime the output is a constant times the input squared, that's always going to be a parabola. Specifically, a parabola with its vertex at what location? Yeah, should be at 0, 0, the origin. So we're going to have a parabola opening upwards because the constant is a positive number, centered at, with its vertex at the origin. Should be completely symmetric in both directions, because the spring doesn't really care whether it's stretched or compressed. It's going to be the same energy-wise either way. And the value of k over 2, the value of that constant determines how steep the graph is. A very large value of k is going to lead to a steeper parabola. Smaller value of k leads to a flatter parabola. So like the difference between this versus this versus this. They'll all have the same vertex. But a weak k value, a weak spring, leads to a very flat graph, almost flat, but not completely flat because it's still a parabola. A stronger spring, a sturdier spring, leads to a much steeper graph. It takes more energy to go the same distance. Any questions on that so far? And we could also graph kinetic energy on that same graph. But before we do, that's going to make the graph look a little bit cluttered. Before we look into kinetic energy on the same graph, let's investigate this whole idea of force and how that relates to potential energy. If we compare a couple of locations on this graph, let's say we're talking about going from, let's say, here to here. In the sense that let's say you have a spring that's currently this long, x initial, and you want to stretch it a little further so it's now this long. So you've got a spring that's already stretched a little bit, and what you want to do is stretch it a little more. So you've got this spring that's already stretched some amount. And you're standing here and you'd like to walk backwards and pull the spring so it's stretched out a little bit more. So you are pulling on the spring to make it more stretched out. In order to do that, what do you have to do? What do you have to apply to the spring in order to stretch it more? Yeah, you've got to apply a force. In fact, in order to even just hold it in place, just hold it in place, you've got to apply a force. If you apply a little bit more force, it'll start stretching. And since you're applying a force as it moves some distance, what do we call a force applied to a moving object? A force including the distance traveled. Yeah, this gets into the idea of work. Just pushing on an object doesn't involve work, but pushing on it as it moves or pulling on it as it moves, that's work. So we can say work equals force times distance. Specifically, the force you applied. So you're applying some force to the object as it moves, and that's equal to force times distance. And when you're doing work, work is just a transfer of energy. And let's say, for simplicity, let's assume that you're gradually stretching this at a constant speed. So you pull exactly hard enough so that it starts stretching at starts moving at some slow speed, and you adapt how much force you're applying so it continues moving at that same slow speed. That means the only type of energy you're changing would be what? Should just be potential, right? Kinetic energy would only be changing if you're changing how fast you're moving. So if you're moving and you're getting faster and faster, or you're moving and you're getting slower and slower. If we assume you're walking at a constant, steady pace, you're not changing your kinetic energy. But you are changing the spring's potential energy because you're making it stretch out more than it already was. So we should assume then, assuming constant speed, assuming you're just walking at a slow, steady pace, the work you're doing is just changing the potential energy. So the change in potential energy is the applied force times the distance traveled. And in order to move at this slow, steady pace, what can we say about the force you're applying? What are you acting against? Why do you need to apply a force in the first place? You're trying to make the spring move, right? But the thing is, if you weren't applying any force, the spring would snap back towards equilibrium. You got to apply, yeah, you're applying a force against the natural force of the spring itself. So you're applying a force to counteract the force of the spring. And we want those forces to balance each other out precisely. If we take a look at the end of the spring, the point where you're gripping it, you're applying a force to the right. So this is the applied force. But you need to apply that force because you're acting against the force of the spring pulling back towards equilibrium. So you got the force of the spring trying to pull back towards equilibrium. You need to apply the same amount of force, but in the opposite direction. That way the total force is zero, so there's no acceleration. The object is capable of moving at a constant, steady speed. And we're going to get into this idea of forces and motion in more detail in 7b. But the key idea here is that if there is a non-zero total force on the object, it's going to accelerate. Its speed is going to change. We want this to move at a constant, steady speed, no changes in kinetic energy. So that means we need the total force to be zero. We need the force of the spring to be precisely balanced out by the force you're applying, which means they're going to be opposites. The force of the spring and the force you're applying are exact opposites. Same magnitude, that is same, magnitude basically just means absolute value for vectors. Magnitude is just how strong it is without caring about direction. So for these purposes, you can think of magnitude as just meaning absolute value. So the applied force is going to be same magnitude as the force of the spring, but in the exact opposite direction. Meaning we can make this substitution. Applied force is the opposite of the force of the spring. And then if you solve this for force, how would you isolate force of the spring here? how would you get F spring by itself? Yeah, if we just divide both sides by delta x. And moreover, I would divide both sides by negative delta x, because we want to get rid of that negative also. So if we just divide both sides by negative delta x, that'll cancel out the negative, cancel out the delta x. So the spring force is negative delta potential energy over delta x. In other words, how much the potential energy changes divided by how far the object travels. If the force is very large, that means it takes a lot of energy to travel a little bit of distance. If the force is very weak, it takes only a little bit of energy to travel some distance. And if there's no force, then it takes no energy at all to travel a distance. You can travel for free if there's no force. Any questions on that conceptually so far? Also, if we take a look at what this actually means on the graph, change in energy, if we're comparing these 2 points, change in energy is how far you go up. Change in x is how far you go to the right. And what do we call that change in energy divided by change in x on this graph?
The slope?
Yeah, that is exactly the slope. So the slope of this line is the force, or rather the opposite of that slope in terms of direction. This is a positive slope, so that suggests there's a force in the negative direction. And indeed, the force of the spring is pulling back to the left, back towards equilibrium. Also, what we found here technically is the average force. The slope of this line from point to point, that is a secant line. Secant line means a line from point to point on the graph. That's not technically the force at any instant. Yeah, that's the average force. Average force is the slope of a secant line. So the slope of a secant line is the average force. And we say average because the force is actually changing. If you're close to equilibrium, the force is weak. The further you get from equilibrium, the stronger the force gets. So that means the force is actually different at each of these locations. But if you're talking about this interval of distances, the slope of the secant line, a line from a point on the graph to another point on the graph, is the average force on that interval, the average force in that region. If you want to know the force at an exact location though, like let's say you want to know the force at this point x initial. Instead of looking at a secant line, what should you be looking at? Yeah, a tangent line. And we can define this mathematically as a limit. If you imagine these points moving closer and closer together, the secant line gets closer and closer to a tangent line. A true tangent line at this point, not a secant line from point to point, but the tangent line that's just barely touching or skimming along that surface of the graph. That tangent line tells you the actual slope, the actual force at that location. So the slope of the tangent line tells you the force at that location. So the slope of the secant line from point to point tells you the average force over some interval. The slope of the tangent line tells you the exact force at that location, at that one instant. And the difference there mathematically is the average force is calculated as change in potential energy over change in x from a location to a location. Whereas the actual force at some location, instead of writing it as delta potential energy over delta x, in calculus, what do we call the slope of the tangent line? What do we call the limit of this as the interval gets smaller and smaller? Exactly, this is the derivative, the exact rate of change, or the instantaneous rate of change at that point. So the actual force is the negative derivative of potential energy with respect to x. Derivative meaning the exact slope of the tangent line at that location, as opposed to the average force, the average rate of change, which is the slope of the secant line. the change in energy over the change in position from point to point on the graph. And which one of these you would use depends on what you want to know. If you want to know the average force over some period of time or over some interval of distance, you'd use this average slope of the secant line from point to point. So you could just calculate how much the energy is changing divided by how much the distance is changing, or how much the position is changing, I guess. Whereas if you want to know the instantaneous force, if you have a formula for potential energy, you could take the derivative of it, or alternatively, you could draw in a tangent line with a ruler or a graphics program or whatever, just a straight line that goes as close as possible to the slope of the curve at that point. Then choose any 2 points you want on the tangent line and measure change in energy over change in position. So that'll give you the slope of the tangent line, which is the derivative of the function, which is the force at that exact moment. Any questions on that so far? And with a little bit of calculus, we can actually find this. We can just say, well, what is the formula for potential energy of the spring itself? That's just the half k times x squared from earlier, right? Half k times x squared. The half of k is a constant, so we don't need to worry about that. But what's the derivative of x squared? Yeah, that'll be 2x. The 2's cancel out. So we get negative k times x. So this gives us a formula for the force of the spring. The force of the spring is negative kx, which means the further you are from equilibrium, the stronger the force is going to be. The stronger the spring is, of course, the stronger the force is going to be. But also this negative means if x is in the positive direction, if the spring is to the right from equilibrium, it gets a force in the opposite direction, back to the left. Or if the spring is to the left of equilibrium, it gets a force to the right. The force is always pointing back towards equilibrium. And we call this a restorative force. It's a force that's trying to push the object back towards equilibrium if it has moved elsewhere. So let's take a look at how we would draw that on the graph itself. Let me tidy up these tangent lines a little bit. Mathematically, we can write it out as the derivative, but conceptually, just looking at the graph, we can also look at it in terms of how steep is the graph, because that's all the derivative really means on the graph. The derivative is the rate of change, which tells you on the graph how steep the graph is, how quickly energy is changing as x changes. So for instance, let's say we're looking at this location. It's moderately steep, and would you say the slope is positive or negative? Yeah, the slope is positive because it's an increasing function. Positive slope, so the derivative is positive, but then we've got this negative sign that reverses it, so the force is negative. If the potential energy has a positive slope, then the force is going to be in the negative direction. So we can draw that, for example, with a arrow pointing to the left. So this would be the force. And we usually write force as an F with a vector sign over it. That little half arrow on top just means this quantity is a vector. Direction matters. But let's say we take a look at a point up here. The slope is still positive, but what has changed? What's the difference between this slope as compared to this slope? As you go further and further out on a parabola, what happens? Yeah, it gets steeper, right? We've got a larger value of slope, a steeper slope. So that means we're going to get a stronger force because the amount of force exactly equals the steepness of the graph. So a steeper slope means a stronger force. We would just draw that as a larger arrow. Or let's say we look at a point over here. What do you notice about the slope at this point? Yeah, we've got a negative slope, which means the force is going to have to be Right. A negative value for slope means the force is going to have a positive value. And the force being positive or negative just tells you direction. A positive force means a force in the positive direction, pointing towards higher x values. And likewise, if we're closer to equilibrium, that's a less steep slope, so it's going to be a less strong force, a weaker force. What if we're exactly at equilibrium? What's the slope at the vertex of the parabola? Yeah, zero slope. And you can see that from the fact that the tangent line would be flat. In fact, anytime you've got a maximum or a minimum, at that max or min, the derivative is zero, which means the force would be zero. Yeah, the magnitude of the force is proportional to slope. In fact, I wouldn't even say proportional. I would just say the magnitude of the force is the slope. The slope, ignoring the negative sign, because magnitude just means absolute value, this slope itself is the force. We don't even need to multiply by any conversion factors or anything. Like if the slope here is, because the slope would be measured in joules per meter, and joules divided by meters actually is newtons. If you look at the units, joules divided by meters is newtons, because joules is kilogram meters squared per second squared, and newtons is kilogram meters per second squared. So if you take joules and divide by meters, one of the meters cancels out, you're left with kilogram meters per second squared, and that's the meaning of newtons. So if you just calculate the slope, like drawing a tangent line and measure between any 2 points on the tangent line, rise over run, that's change in energy divided by change in position. Newtons or joules divided by meters is newtons. So the slope is the strength of the force as an absolute value. And then the positive or negative is just telling you the direction of the force. But notice that all of these forces are pointing towards what? What are these all pointing towards? Yeah, they're all pointing towards equilibrium, which is the low point on the energy graph. And in general, the force is going to be pointing towards lower potential energy. So for the spring, the local low point for potential energy is the equilibrium. So all the forces nearby are going to be pointing towards equilibrium. You stretch the spring to the right, you get a force pulling it back to the left. You compress the spring to the left, you get a force pushing it back to the right. So it's pointing towards equilibrium. And this is true for other forms of potential energy as well. For example, gravity. Which direction does the force of gravity pull? If you just got some object, yeah, the force of gravity is pulling it downwards. And as an object moves in that direction, what happens to its gravitational potential energy? It decreases, right? The force of gravity is pulling you from a high potential energy zone towards a lower potential energy zone. And this is generally true for any force associated with a potential energy. If you've got some region that's high potential energy, and you've got some other region that's low potential energy, the force associated with that potential energy is always going to be pointing from the high potential energy zone towards the lower potential energy zone. And the more different the energies are per unit of distance, the stronger the force is going to be. That's really all this negative sign means. The derivative is telling you that the amount of force depends on how quickly the potential energy changes from point to point. Not as time passes, but how much it changes per meter. And the negative sign is all about direction. This negative sign can be interpreted as the force is pushing or pulling in the direction opposite to the increase in potential energy. In other words, it's pointing towards lower potential energy. Force of gravity is pulling you from the high potential energy zone towards the lower potential energy zone. The force of the spring is pushing or pulling towards equilibrium, which is the lowest potential energy zone. Any force associated with a potential energy is going to be pushing or pulling the object towards lower potential energy. Or we would say in the direction of decreasing potential energy. Sometimes that's also called, it's pulling in the opposite direction of the gradient. Gradient just means the direction of increase in the value. So for instance, for gravity, the gradient would be upwards because that's the direction in which gravity potential energy is increasing. Right, this is not going to be the same for kinetic energy. The force here we're saying is directly related to potential energy because this is, for instance, let's say a spring force that's associated with a spring potential energy, or a force of gravity associated with gravitational potential energy. Or later on, we're going to be looking at an electrical force associated with electrical potential energy. But this does not relate directly to the kinetic energy. That's going to be different. In part because what's the indicator for kinetic energy? Yeah, indicator for kinetic energy is speed. This is not a graph of speed versus energy. This is a graph of position versus energy. So kinetic energy can certainly be graphed on this. At every location, the object has a speed. But since we're not graphing speed versus energy, the slope of this is not going to be meaningful for kinetic energy. The slope is meaningful for potential energy because potential energy depends on position. So a graph of energy versus position is going to have a very strong meaning for potential energy because potential energy depends on position and force, which is why force is the slope here. So we can certainly graph kinetic energy on the same graph because at each position, the object has a speed. But the graph is not going to be meaningful in the same way because it's a graph of position versus energy, not speed versus energy. Any other questions on this idea of force so far? One other interesting thing on the graph I'd like to take a look at, if we had a graph that was shaped differently, let's say we had some different kind of potential energy that was an upside down parabola instead. Let's say our potential energy graph happens to look like this. So not a spring, but something else entirely. If we made an energy interaction diagram, it kind of depends on what else is happening. If you're talking about just that person gradually pulling on a spring at a constant speed, then kinetic energy is not changing. You're doing work to change the potential energy, and there is no change in kinetic energy. But if you're talking about just like the object oscillating on its own, then that means the kinetic energy and potential energy are both changing, and there's no work being done. So it would be a closed system. If we have this upside down potential energy graph, though, just some hypothetical different kind of energy, let's take a look at the forces there. If you're exactly at the top here, what's the slope? Yeah, the top here is still 0 because the tangent line is flat. So that means at that point, the force is 0. You got no force at all at any max or min because the tangent line is flat. But what about, let's say, over here? What can you say about the slope at this point? Yeah, the slope is negative. In fact, this entire half of the graph has a negative slope, which means the force has to be in which direction? Yeah, we have a positive direction force. And note that that force is pointing in the direction of decreasing potential energy. It's a force to the right, and if you move to the right, your potential energy decreases. Same thing here. It's still a negative slope, so we still get a positive direction force. But since it's steeper, we get an even stronger force. Or if we're up here, it's still a negative slope, so we still get a positive force, but it's a pretty flat slope, so we get a weak force. What about over here? What's the slope in this region? The slope, if you go left to right, you're increasing your value. So the slope is going to be positive, right? We've got a positive slope, but that means the force is going to be, negative. The force is always the opposite of the slope. So a positive slope on the potential energy graph means a force in the negative direction. So for instance, here it's just going to be a little bit negative, and then here it's a steeper positive slope, so we've got a stronger negative force. Here we've got a very steep positive slope, so we're going to get a very strong negative force. And again, these are forces pointing towards lower potential energy zones. The further we get to the left, the lower the potential energy gets, so the force is pointing towards that lower potential energy zone on both sides. So those would be what the forces look like in this case. And if we take a look at what's going on at this maximum here, in both of these cases, this point and this point both count as equilibrium, because equilibrium just means a location where the force is zero. If you start with the object there and staying still, it'll just stay there forever, because no force means it doesn't change its motion. So both of those points count as equilibrium. Meaning that at that location, the force is zero. If the object is at that location and staying still, it'll just continue staying still. It'll stay there forever. But it's very useful to look at what happens near equilibrium also. What if you have an object at equilibrium and you move it a little bit to the right? What's going to happen to it? If you've got an object that has moved a little bit to the right, which direction is the force on it now? Yeah, it gets a force in the negative direction, which means it gets pushed back to the left. If an object is a little bit to the right, it gets pushed back to the left, back towards equilibrium. Or what if the object moves a little bit to the left? Which direction does it get pushed? Yeah, it gets pushed back to the positive direction. So anything near equilibrium gets pushed back towards equilibrium. If you're a little bit off to the right, you get pushed back to the left. If you're a little bit off to the left, you get pushed back to the right. This is why we call this a restorative force. A restorative force is trying to restore the equilibrium situation. It's pushing everything back towards equilibrium. And we would call that a stable equilibrium. Stable in the sense that anything at equilibrium stays, equilibrium just means anything there will stay there forever if it's not moving yet. But stable in the sense that if it wobbles a little bit, it gets pushed back towards equilibrium. The forces are trying to maintain that equilibrium. On the other hand, in this case, if you're exactly here, you stay there forever. That's why we call it equilibrium. But what happens if you go a little bit to the right? What do the forces do to you? If you're a little bit off, a little bit to the right, the force pushes you in which direction? Yeah, more further in the positive direction. The force is pushing you to the right. So if you're not quite at equilibrium, if you're a little bit to the right of equilibrium, the force pushes you further away from equilibrium. Or if you're a little bit to the left, if you're at equilibrium and then wobble a little bit to the left, do the forces push you back towards equilibrium or do they push you further away from equilibrium? Yeah, you get a force in the negative direction, pushing you further away from equilibrium. So this would be called an unstable equilibrium. It is technically still equilibrium because if you're exactly at the center and at rest, you can stay there forever. But if you go a little bit off one way or the other, the forces push you further away from equilibrium. And I think this is very much like the difference, the difference between being balanced at the bottom of a valley versus being balanced at the top of a hill. Not just because these graphs look like this, but because of the behavior it creates. If you're balanced at the bottom of a valley, you can stay there forever. But if you move a little bit one way, gravity pulls you back towards the bottom of the valley. So that would be stable equilibrium. If you're balanced at the top of a hill, if you're exactly at the top, exactly balanced, you can stay there forever. But move a little bit one way or the other and you're going to roll further down the hill. You get pushed away from equilibrium. So that would be unstable. So those are important things to look for. In general, if the potential energy graph has a minimum, a low point, all the nearby forces are pulling towards that lower potential energy. So that would be stable equilibrium. If the graph of potential energy has a local high point, a local maximum, then all the forces nearby are pulling away from that point because they're pulling towards lower potential energy. So a maximum on the potential energy graph is going to represent unstable equilibrium. Any questions on that so far? Positive and negative for forces are just talking about direction. If the force is positive, that just means it's pulling or pushing towards higher x values. Negative force just means it's pulling and pushing towards lower x values. So it really just is telling you which direction the force is pointing, the direction of the push or pull. Any other questions on that? And I think this will help you make a lot more sense of that quiz question, because that just shows you a graph of potential energy versus x. And it's asking, at these various different locations, rank the magnitudes of the forces. How can you tell how strong the force is if you've got the potential energy graph? What determines, or how can you tell where the force is stronger versus weaker? Like if I just give you some graph of potential energy and say, is the force stronger at this point or at this point? How would you check? Yeah, you take a look at the tangent lines. And you don't necessarily even need to draw in the tangent lines. It can sometimes be useful to do just to visually verify. But all you really need to do is check where is it steepest. Like in this example question here, we have this graph. If we want to know or compare the forces at these 3 points, it looks like at location A, we've got a tangent line like this. At location B, the tangent line is going to be flat. At location C, the tangent line looks like maybe like this. Yeah, something like that. So which one of those looks like it's the steepest slope? Yeah, it looks like C is the steepest slope, so we would say the force is strongest at C. And then A, it's a little bit less steep, ignoring the direction for now, ignoring whether the slope is positive or negative. At A, the slope is a little bit less steep, so that would be a slightly weaker force. And then what would be the force at location B? Yeah, at B, there's zero force. There's no force at all because the tangent line is flat. Or there might be some forces, but they cancel each other out, and the total force is 0. And B would be equilibrium because the slope is 0, or the force is 0. Would you consider that to be stable or unstable equilibrium? What do you notice about the forces nearby? Like, let's say you're a little bit to the left of B. Do you get pushed away from B or towards B? Yeah, you're going to get pulled away because forces push or pull you towards lower potential energy. If you're at this location, the local force is going to pull you towards the nearest local low point. So that's pulling you away from that equilibrium. And likewise, if you're on the right side, you get pulled towards the local low point. So that means location B is technically equilibrium, but it would be an unstable equilibrium. Whereas these two minima at x equals 2 and x equals 6, those would be stable equilibrium because any points nearby, you get forces pushing or pulling you back towards equilibrium, towards that low point. Any other questions on that? So that's the basic idea here. The core concept that the force is the slope of the potential energy graph, except in the opposite direction. Positive slope means negative force, negative slope means positive force. So keep that in mind as you look through these practice quiz problems and also on your FNT problems. There's a lot of stuff on the FNT talking about like, given this information about forces, try drawing a potential energy graph. So try that out. I find it's often helpful to just make a list of everything you know about the force, like where is it strong, where is it weak, which direction is it in, and then try translating each of those statements about force into a statement about the potential energy graph. Like the force is strong in this region means the potential energy graph is steep in this region. The force is pointing in the negative direction in this region means the potential energy graph has a positive slope in this region. No force at this location means potential energy graph has 0 slope at that location. So try making a list of properties you know about the force, translate those into a list of properties you know about potential energy's slope, and then try drawing a graph of potential energy that has those properties. Good way to get some practice with this. I'll post a recording later today, maybe in a couple of hours, I think. And that link will be on the math.ncheese.org as usual. Anyway, let me know if you have any other questions by email, and I will see you next time. You're welcome.